This is an interesting problem, and let's see how we can solve it with an ordinary mathematics. So let's say I am start trying to solve it in I square it, so you get x plus 1 upon x whole square, that is also going to be 1. And I want to see how far I can go, because this leads to x square plus 1 upon x square plus 2 equal to 1, and this will give x square plus 1 upon x square equal to minus 1. That is one thing. Then I notice that from here do I go? Where do I go from here? For example, if you try multiplying this and this, you notice that x into x square will give you the x cube, and 1 upon x multiplied by 1 upon x cube, 1 upon x square will give you 1 upon x cube, and there will be the other terms. So let's go ahead and do that. If I multiply this equation with this equation, I get x plus 1 upon x multiplied by x squared plus 1 upon x squared equal to 1 into 1 is minus 1. And from here I get x cube plus 1 upon x cube, and then if I multiply x with 1 upon x square, I get 1 upon x, and if I multiply 1 upon x with a square, I get 1 upon x. So this is plus x plus 1 upon x equal to minus 1, and this has a value of 1, so I get x cube plus 1 upon x cube is equal to minus 2. One thing when doing this, we realize that it's possible to find a higher order by multiplying subsequent squares of x. So what I mean to say is, let's say if I multiply x to the power n minus 1 plus 1 upon x to the power n minus 1 with x plus 1 upon x, to see if I can get, because the idea is, and see what we get from this one. So the key idea is we now have to find a very high order, and if I keep going on this, it's going to take forever. So we want to know how does x to the power n plus x to the power n looks like. And let's say we have x to the power n minus 1 and x to the power plus x to the power 1 upon n minus 1. If you multiply this, you see this is x to the power n plus x to the 1 upon x to the power n by multiplying 1 upon x with 1 upon x to the power n, and then you multiply x with 1 upon x to the power n minus 1, so this becomes, let's say this multiplied by this, we get 1 x to the power of n minus 2 plus 1 upon x to the power of n minus 2. And x plus 1 upon x is nothing but 1. So what we get is x to the power n minus 1 plus 1 upon x to the power n minus 1 equal to x to the power n plus 1 upon x to the power n plus x to the power n minus 2 plus 1 upon x to the power n minus 2. And that means that I can express x to the power n plus x to the power 1 upon x to the power n as this x to the power n plus 1 upon x to the power n minus 1 minus x to the power of n minus 2 plus 1 upon x to the power n minus 2. So this is a recursive function where we can say that fn is equal to fn minus 1 minus fn minus 2, and it keeps going on. And from here, since we know that, let's say let's call this one f1. f1 is equal to 1 and f2 is we already calculated it, minus 1. Then f3 is going to be f1 f2 minus f1. So this is going to be minus 2, and this is what we confirmed. We already calculated this. To find f4 is going to be minus 2 minus minus 1, so this is going to be minus 1. And then f5 is equal to this minus this, so this is minus 1. Actually plus 1, minus 1 minus minus 2 plus 1. f6 is equal to this minus this plus 2, and then f7 is equal to 2 minus 1 is 1. f8 is going to be f7 minus f6 minus 1. f9 is equal to minus 1 minus 1 minus 2. f10 is equal to minus 2 minus minus 1, which is minus 1. f11 is again plus 1 minus 2, and f12 is going to be 1 minus 2. Now if you see this, the sequence is repeating, and by this same work it is going to repeat every 6 times. With this observation, I could have stopped here, and if I am a programmer, I could write a code which will iterate a loop 2021 times and get me the result. But since you know this, now it's easy to find x to the power 2021. So how does it look like? So one thing we notice that, let's say if I divide 2021 by 6, I get 300, and I want to see what's the remainder when I divide it by 6. So it's 18, 2, 2, 3, 4, 1, 6, and plus 5. Okay, this is how it looks like. So this is going to cycle 336 times, then we will be here, and then there will be 5 more power. So I can think of that if I iterate these things is 1, 2, 3, 4, 5. This is going to be its value when it's going to be to the power of 5. So the answer is going to be 1. So this is how we could solve it in a recursive way. But there are other ways to solve this question, and if you are interested, I'll give some pointers that you can use to see. This is how a computer programmer would like to do it, or a recursive thing. But there are pure algebraic ways as well, and if you know the Euler's function, you could do that as well. So let's take a look at how you could do it using a pure algebra thing. So for example, you notice that x square minus x plus 1 is equal to 0, and you can solve it as a quadratic equation where you will get imaginary roots. But our key idea is to see if any higher power of x, we can get some simpler number. So what I do is I can multiply this equation with x. Let's say x plus 1 multiplied by x squared minus x plus 1 equal to 0. And if you notice this I can write x cubed plus 1 equal to 0. This equation has 2 roots, and this equation has 3 roots. Now any solution of this one must also satisfy this as well. So let's say this one has roots of alpha and beta. Then alpha and beta must satisfy this equation as well. For example, the roots of this equations are x equal to minus b plus minus square root of b square minus 4ac upon 2a, or 1 plus minus square root of minus 3 divided by 2. Now these, if you fit in these two values in this equation will also be satisfied. So where do we go from here? Any root of this equation must satisfy x cube is equal to minus 1. Now what I do is, let's say if alpha is a solution to this equation, then alpha must be an equation to this equation. So from here what I do is I write this equation as x to the power of, now I divide 2021 by 3 to see if it's divisible by 3 or not. So I get 3 7 times 21, 1 plus 2. This is what I get. So I can write it as 3 to the x to the power of 3 whole to the power of 673 multiplied by x square, okay, plus 1 upon x to the power 3 to the power of 673 multiplied by 1 upon x square. This is what we have now. Now this thing we know is minus 1. So I have minus 1 multiplied by x square, and this is minus 1 multiplied by 1 upon x square. This becomes minus of x square plus 1 upon x square, and we just notice x square plus 1 upon x square is minus 1. So minus 1 into minus 1 is plus 1. But this is another algebraic way to solve this question. Now for those who know Euler's function, I'll just point it out. I will not solve this completely. Is that you can express this as e to the power of I theta, and then you expand it in terms of cos theta and sin theta, and thereafter powering becomes easy. I will not cover it. You can take a look at that.